Good morning, students. Today, I'm going to introduce you to a very powerful axiom of this real analysis that's known as completeness axiom. This completeness axiom, and this completeness axiom is also sometimes called LUB axiom, least upper bound axiom also. What it implies, it means that every bounded from above subset of real numbers R has a least upper bound, in R. This is the statement, and this is the statement of a completeness axiom of real numbers, and it tells us, it gives us the guarantee of the existence of a least upper bound of a set which is bounded from above. But we do have its counterpart for sets which are bounded from below, and say that follows from this statement. How it follows? We have this relation between supremum and infimum of a set, that infimum of any set can be computed. You must verify this, that this is supremum minus of supremum of minus of A. You must verify it. And from this it follows that since any supremum of supremum of minus of A, and its minus is going to be an infimum of the set A, and if A is bounded from below, if A is bounded from below, then minus A is obviously bounded from above, because minus, when you multiply numbers by minus, it reverses the orders, is bounded from below, and hence from the axiom of completeness we see that minus A has a supremum, say, suppose its supremum is U. This implies that then uh, minus of A is less than or equal to U for all A in A. And this further implies that if you remove this negative A, minus of A, you will get A greater than or equal to U minus of U for all A in A. And this minus U is then the infimum. This can be proved without any much requirement, anything that's I left to you to verify that this minus U is actually infimum of A. And C, this minus U is actually nothing but this is minus of supremum of minus of A, and this establishes this equality. So now we can state with the help of this that so we have this statement now, that every bounded from below subset of R has a least upper bound, has a greatest lower bound, has a greatest lower bound in R. So that means the counter statement for bounded from below also holds of the completeness axiom, and combining these, that means finally you can say if you have a bounded set, with then that bounded set is a bounded from above and bounded from below also. So we can write in the directly here as a consequence of this completeness axiom that every bounded subset of R has its supremum and infimum in R. So this is a statement, this is the final that we can deduce from this completeness axiom. Now, this R along with this axiom is known as a complete ordered field, since we have seen already that R along with addition, binary operation addition and multiplication is a field, and then it has a ordering on it, total ordering on it, it becomes a totally ordered field. It becomes ordered field. And along with this axiom, which says that every bounded above set has a has a least upper bound, and this R is now known is called complete ordered field. It is called complete ordered field. Now the question is that if we have another field here, we know that that set of rational numbers is also an ordered field. Is also an ordered field. All the properties of field and this ordering are valid on set of rational numbers also. So it is an ordered field, but we are going to establish that it is not complete. That means that is completeness axiom. Completeness axiom fails on this Q. How it fails? To establish that it fails, let's consider a subset of Q which is bounded above, but it doesn't have a supremum in Q. So let us consider a set S of those rational numbers whose square do not exceed 3. So this is a subset of rational numbers, and it is clear that 1 is an element of this set S. This implies that S is a non-empty set. So we have a non-empty subset of S. Now let us check whether it is a bounded above. In particular, let us take some element alpha. Let me choose some other notation. I have to use again alpha somewhere. Let me take comma be a rational number such that its square is greater than 3. So such rational numbers do exist. For example, 2 is one of the such rational numbers. So there is no problem, there is no loss in choosing such a gamma. Then this gamma is an upper bound. It's an upper bound of S. Why it is an upper bound of S? See, what you have, this gamma square is greater than 3. Now suppose it is not upper bound. Suppose it is not an upper bound. If it is not an upper bound of S, that means there must be some element which is not smaller than this gamma. So there is some element in S such that this X is greater than gamma. Now see, but I'm going to take this gamma to be a positive number. So I will write it here, Q plus that gamma is a positive rational number whose square is greater than 2. So there now this gamma is a positive number. So X is also positive. And then this implies that square of X is also greater than gamma square, but gamma square is greater than 3. This implies that X square is greater than 3. But you see that X is an element of S, and any element in X S has square less than 3. So you have this contradiction now. Its square is also greater than 3 and less than 3. It is not true. It is absurd. So this forces us to accept that this gamma is an upper bound of S. Now gamma is an upper bound of S, so S is a bounded above set. S is a bounded above set. Now the task is to establish that S do not have a supremum in Q. It has a supremum or not, but it for sure it doesn't have a supremum in Q, and we are going to establish it. And we suppose on the contrary that there exists a supremum denoted by alpha of this set S, and that supremum is well in Q. We suppose this thing, and then we have to reach at a contradiction to not accept this contrary as this assumption. Okay, now clearly S has positive elements, like 1 is an element of S, so its supremum cannot be negative. So clearly, if it has a supremum, then alpha has to be positive. And let us define an element beta is equal to 2 alpha plus 3 upon alpha plus 2. And so clearly then beta is a positive number because alpha is positive, and beta is a rational number because alpha is a rational number, and alpha is a field. So this is all the combinations of addition and multiplication of alphas and 3, 2 and other numbers with alpha. So it is a rational number. Now let us look at its square. Let's estimate the square of beta and see whether it is bigger than 3 or not. But before that, let's record the possibilities that we have. We have the following, the exhaustive possibilities. The following possibilities. What are the possibilities? Square of alpha can be less than 3. Square of alpha can be 3. And square of alpha can be greater than 3. We do not have any other possibility, but let me rule out this second one. When alpha square is 3, alpha being a positive, alpha will be square root of 3, but look at this, square root of 3 is an irrational number, which is a contradiction to our assumption that alpha is a rational number. So this possibility is ruled out. Now we will find this alpha square less than 3 and alpha square greater than 3 also, that no such possibility occurs. Then this will lead us to the contradiction that if no such possibility occurs, then where is the ordering? Then ordering fails, and this leads us to discard the assumption that alpha lies, that the supremum lies in Q. So for that, first let us look at beta square minus 3. So beta is 2 alpha plus 3 square minus alpha plus 2 square minus 3. It has to be, you just expand 2 alpha plus 3, it has to be 4 alpha square minus, it has to be plus 12 alpha minus 9 minus 3 times, you just take out the LCM, it has to be alpha square plus 4 plus 2, 4 alpha. And in numerator you have alpha plus 2 whole square. What is this thing? This is 4 alpha square minus 3 alpha square, it will be alpha square. 12 alpha and 12 alpha will cancel out if you remove the bracket and multiply by 3, then, and it has to be plus 9, and plus 9 and minus 12, it will be minus 3, and you will have alpha plus 2 whole square. Okay, you have this situation. Now look at this. when alpha square is less than 3, then obviously this number is negative. That means beta square minus 3 is negative if alpha square is less than 3. That is beta square then is less than 3, and for alpha square less than 3, and beta square, when alpha square is bigger than 3, so beta square is going to be greater than 3 if alpha square is greater than 3. This is the situation. Alpha square greater than 3, beta square is also greater than 3. Alpha square less than 3, beta square is also less than 3. Okay, this is done. That means the ordering of alpha square with respect to 3 is going to be same of beta square with 3. Now let's look at beta and alpha. Now beta minus alpha, which one is bigger? We have 2 alpha plus 3 upon alpha plus 2 minus alpha. You have 2 alpha plus 3 minus alpha square minus 2 alpha, and you have alpha plus 2, and this is equal to, you have 2 alpha to alpha cancel with this 3 minus alpha square upon alpha plus 2. So you have, now let me make a table. Alpha square less than 3 and alpha square greater than 3. Now when alpha square is less than 3, you can see that beta minus alpha is a positive quantity. That means in that case you have beta minus alpha being a positive means beta greater than alpha, and in case of alpha square greater than 3, oh sorry, alpha square greater than 3, then 3 minus alpha square is going to be a negative quantity, and then hence beta is going to be less than alpha. Okay, but for alpha square less than 3, what we had that beta square is also less than 3, and alpha square greater than 3, the square of beta was also greater than 3. Now what is alpha? Alpha is supremum of S. Alpha is supremum of S. So let us look at this first case then. Uh, Beta square less than 3 implies that by definition of S, beta is an element of S. Now beta is an element of S which is bigger than the supremum of S. This whole box, it leads us to a contradiction, because no element of S can be strictly bigger than its supremum if its supremum exists. We had assumed that alpha is its supremum which exists. So if such as alpha exists, how beta can be strictly greater than its supremum? So this is a contradiction. And likewise, in the beginning, I established that any positive number whose square is bigger than 3 is an upper bound of S. Now what do we have a situation? I have a beta. That means beta is an upper bound, and from here we see that this beta is an upper bound which is strictly smaller than alpha. This is again a contradiction, because no upper bound can be bigger than its supremum. So in every situation, in every case, we arrive at a contradiction, and hence this gives us that, hence it implies that S has no least upper bound in Q, and this proves that complete ordered field. Yes, it is okay. So now you have this completeness axiom, and you know that there are fields which are not complete ordered fields. So it kind of gives you a justification that okay, R is something special, R has some speciality in it. And now let us look at some other small exercises. One of the thing that needs a verification from students side is that subset of a bounded set is a bounded set. set, and it clearly follows that every bound of a superset is going to be a bound of a set. But what I'm going to show, what I'm going to establish, what I'm going to focus on here is that if A is a subset of B and B is a bounded set, B is a bounded set, then by the completeness axiom, supremum and infimum of B exists, and so does that of A and B, because A is also bounded now. And then we want to establish, check out that what is the supreme, what is the relation of the supremum of A and supremum of B and infimum of A and infimum of B. Now look at now we see that supremum of B, which is an upper bound of B, so is an upper bound of A also, upper bound of A. If it is an upper bound of A, then by the definition of supremum of A, it has to be smaller than this all of its upper bounds. So in particular, it is smaller than the supremum of B. Similarly, likewise, we see that infimum of B is a lower bound of B. So it is a lower bound of A also. It's the lower bound of A, and hence infimum of A, which has to be the greatest among all the lower bounds, and this has to be greater than or equal to infimum of B also. So you have this relation now that A subset of B, then you have this thing. One, supremum of A will remain less than or equal to supremum of B, whereas in case of infimum you have a different ordering. You have this thing. You need to keep this in mind. And when set gets smaller, the infimum gets bigger, and when set gets bigger, the supremum also gets bigger. Okay, or the other way you can say that when set gets smaller, supremum also gets smaller, but whereas the infimum becomes bigger and bigger the moment your set becomes smaller and smaller. So this is all about that I had to talk about today, and rest we will see in the coming lectures. See you then. Bye.